Welcome everyone. Thank you very much for joining the Rise Easy Computer Engineering Distinguished Speakers webinar today. So before introducing our speaker, let me briefly go through some logistics. So first, if you have questions during the talk, you can message me in the Q&A chat. At the end of the talk, we will select those questions to be answered by our speaker. Meanwhile, during the talk, I will also monitor the Q&A chat in case there are questions that would be better to be clarified or addressed in the middle of the talk. Second, this talk will be recorded and uploaded to our department's YouTube channel for future access. Next, it's my great pleasure to introduce today's distinguished speaker, Professor Diana Marculescu. Professor Marculescu is currently a chair professor and department chair in the EC department at UT Austin. Before joining UT Austin, she was also a chair professor and associate department head of the ECE department at CMU. She received her PhD degree from the University of Southern California. Her research interests include energy-aware and reliability-aware computing, hardware-aware machine learning, and computing for sustainability and natural science applications. She has received numerous awards and recognitions for her outstanding research and leadership, including the following: the NSF Faculty Career Award, several Best Paper Awards, the ACM SIGDA Technical Leadership Award, the Mackey Institute Technology Georgie Tolman-led Research Award, being selected as an elite fellow, a distinguished lecturer of the IEEE Circuits and Systems Society, the Molly R. Pitts-Deely Women in EDA Achievement Award, and selected as a fellow of both ACM and IEEE. Finally, on a personal note, Professor Marculescu has been an exceptional role model in the community for both her research and leadership. Thank you, Diana, for agreeing to spend this time with us. The rest is all yours.
Thank you. Thank you for the invitation. I really appreciate everyone attending my talk. I'm a bit sad that I can't be there in person, but I guess we're all sad that we cannot meet in person due to the current circumstances. So I'm really delighted to be here. I'm looking forward to hearing your questions. And one thing I would like to, so the title of my talk is Putting the Machine Back in Machine Learning. And it's all the work that I've done in collaboration with my students, some of whom are at Carnegie Mellon, and many collaborators at both Carnegie Mellon as well as Microsoft and Google. And the title of my talk might seem like the machine left machine learning at some point. It's not quite like that. The reason why we're talking about machine learning, and many of us are working in this space, especially at the boundary between computer systems and machine learning, is because the progress in computer systems has made it possible. And as we all know, GPUs actually made possible for us to talk about deep learning and all the great applications that that this kind of modality has. So without further ado, I'm going to start with a motivating example. So if you are trying to basically query your smartphone or your smartwatch when they're off network, and you ask very simple questions, and this is an actual scenario that I've tried. What is 100 divided by 2? What is my name? Or what is Apple? You are basically not going to get an answer if none of your devices are connected to the network. So this is actually a screenshot of my actual watch. sorry, I'm not able to help you right now. Please try me again in a bit. And the reason for that is because all these applications that require speech recognition, and particular machine learning for speech recognition, run in the cloud. The goal of our research is to actually push all this to the edge. And the reason for that is multi-pronged. We would like to be able to do this without the ability of having, or without the need to having to query these through the cloud, without having to go through the latency involved in that, and without privacy constraints regarding the data exchanged. So if you look at where we are in terms of machine learning applications, there's a wide variety and wide spectrum, and here I have very few of the many examples that we see. They all push hardware to its limits. So if you think about deep learning models and the way they're used in most applications, in automotive, for example, in autonomous driving, object detection, or in smart home and security. Nest is a prime example of where machine learning has been used in the early days to understand and learn the behavior of a house occupants, for example. Mobile and wearables that allow us to, or help us in every activity, as well as drones or VR, AR applications. All of these require quite a lot of computing resources. And the reason for that is deep learning models, as you know, are complex. We talk about deep learning, meaning there's a lot of layers that these machine learning models have, and that requires quite a bit of computation, quite a bit of memory usage. So if we would like to push this to the edge, we are going to incur quite a bit of overhead. So indeed, hardware constraints are a limiting factor in pushing deep learning applications or mobile platforms. To give you an example, some of the early work published in CVPR in 2017 showed that the task of object detection would drain the smartphone battery in less than an hour, right? And I said early work, 2017 is early, and it's actually ancient in machine learning time because things happen very fast, and it's a very dynamic field. In addition, you do have the edge cloud communication constraints, right? So unless you're networked, you're on network, and you are connected to the cloud, you're not going to be able to run that task that you would like to run locally. Maybe it doesn't fit to on your device, so you have to run it in the cloud. But then you are subject to communication constraints. Is the network on? Is the network running properly, or the quality is not as great? And finally, even though you might be able to do that query, you do have response time constraints. Of course, when you do object detection, or maybe you're in a video scenario, in that case, the response time plays quite a bit of a role, and large response times will introduce low quality of service and user experience. So all of these take us to the place where we would like to be able to push these complex machine learning models to the edge, but we need a different approach. We need a way to customize them to the edge, but at the same time, try to see whether the hardware that runs on edge devices could be customized to run machine learning applications. And we all know about accelerators, so hardware that is designed for machine learning, but also machine learning that is amenable to run on edge devices. That's where the idea of co-design comes into the picture. So we do have a challenge in designing these deep learning models under hardware constraints. And the reason for that is when you think about identifying deep learning models that have optimal learning performance, when I say performance, I mean accuracy, the goal of finding that is really a complex hyperparameter optimization problem. So typically, what you need to identify is number of layers, number of units and their type. You have learning rate, and then the goal is to maximize the classification error, for example, or other types of object detection accuracy metrics, right? So typically the loss is what you're looking after. The challenge with that is that you're going to end up with quite a bit of a search space. So you're going to have with a lot of deep learning models with different hyperparameters. So what your goal would be to identify these models that live here at the lowest classification error space. However, if you introduce hardware constraints to this search space, the problem becomes even more complex. Let's pick energy consumption as a hardware metric. In that case, you can get up to 40x difference between these models. So you will get quite a few of range in terms of both accuracy as well as energy cost. And the same is true for latency or memory footprint or flop count, right? The number of floating point operations that your model requires. They all translate into computing resources. So the question is, how do I identify in this huge search space these configurations that allow us to maximize accuracy and minimize energy cost, or minimize response time, or minimize the memory footprint? So we need a way to efficiently parse this space. And to give you an idea of how hard this is again data from a paper published 3 years ago in 2017 that shows that to be able to identify just looking at accuracy, the models that have this highest accuracy would require going through 12,000 models on 800 GPUs on 28 days. This is the equivalent of 62 GPU years. This is enormous, right? So this is where the idea of neural architecture search came into the picture, where we do a smart search of this space. So we don't take years or weeks, we at least reduce it to days, and you'll see later, we're actually able to reduce it to hours. So the idea is to look at that space, do an efficient search, but at the same time, introduce hardware constraints. Now, what should be our steps? So we view the way this should be approached from 3 different components. Modeling of these hardware metrics on these machine learning models. And the reason we start with modeling of these hardware metrics is because typically you cannot optimize what you cannot measure. So if we want to identify machine learning configurations that do not exceed a certain energy or memory or latency constraint, then we need to be able to estimate how long will it take to do an inference or how much energy it will cost. So the first component is this energy or hardware metric in general estimation. And the way this starts is by looking at the joint search space. So typically a deep learning practitioner would look at the design space for the machine learning model, right? So what are the components? Am I using convolutional layers? Am I using fully connected layers? Am I using skip connections like for residuals? Am I using a different kind of convolution that is, for example, using Mobile net networks? From the perspective of hardware designer, we do have hardware constraints, and we need to come up with ways to identify the hardware. So you have hardware constraints and you have deep learning objectives. When you put everything together, the problem becomes more complex. However, we start with the modeling part first, which is modeling the hardware metrics that we can do once and then reuse over and over again. So we adopt this approach, NeuralPower. So NeuralPower allows you to accurately model power, energy, latency for deep learning models running on hardware platforms. And these can be used both as an objective and as a constraint. So you can use it as an objective when you want to minimize or maximize energy efficiency, or as a constraint when you want to find models that are provide maximum accuracy but satisfy the hardware constraints. So let's go in more details. The way this is done is by looking at ways to model on a per layer basis the different types of neural architecture compounds. So typically machine learners start with with a CNN architecture and then try to iterate, right, to identify the configurations that satisfy certain accuracy. But what we're trying to do is in this loop where machine learners try to identify these configurations, we try to see which ones will be able to satisfy these hardware constraints. So the way we build the NeuralPower framework is by building layer level models for latency and energy and power, compose them into network level models, and then do so in a target software hardware platform specific fashion. And then once you do that, you have detailed power, energy, latency breakdown. So that's the big idea. So to give you an example, the network level models for energy, we have the sum across all layers. So it's on a per layer basis of the average power per layer times the latency per layer. And that's your, it can be used to also fit total latency, end-to-end latency, as well as power, average power. So once we have the per layer models, we can come up with network layer models. Runtime is just the end-to-end latency summed up across all different layers. And the average power is this from here, from the top, you can see that the average power is basically the total energy of all the layers divided by the total end-to-end latency. So these are clear, well-known definitions. So how do we come up with these per layer models? So layer level models are basically relying on a combination of polynomial models and an addition of a few terms that are related to the type of computation that we're doing, so flop counts and things like that. So what we do here, we do model selection of the various components in this model. The feature space for the runtime models include kernel size, stride size, padding size, so on and so forth. These are typical parameters for convolutional layers. For every type of layer, these would be different. But the idea is I'm giving you here an example of conv layer type of runtime model. So we basically fit this model. We do model selection by gathering a lot of data about per layer latency as a function of the various feature space parameters. In a similar fashion, we do model selection for power. And the way we gather data is by constructing these synthetic CNNs that allow us to build these power and runtime models for each type of layer. And you do this characterization once, and then you can use it over and over for that particular hardware platform. And the results I'll show are for one hardware platform, but in our work, if you read the paper, and actually one of my students included even more in his PhD dissertation, this is extendable for multiple hardware platforms, and it's a methodology in effect. So how do these layer level results compare with actual measurements? So I'm giving you a few examples here for convolutional, fully connected, and fully layers. NeuralPower is our work. And we just have the model size here for these examples. NeuralPower achieves anywhere from 11 to around 40% with mean square percentage error, compared to prior work, which is much less accurate. And also in absolute, the absolute error in milliseconds is on the order of 1 millisecond or less. So this is very encouraging because it allows us to provide more accurate results. Similarly for power, it's again very close. The accuracy in this case is much better. It's 90% accuracy, meaning the percentage error is 10% or less. And the difference, the actual absolute difference in power watts is again sufficiently small. So how would these kind of results be useful to others? So suppose you are a machine learner, or maybe you are a hardware designer, and you want to identify how you can design your machine learning model such that you satisfy, say, latency constraints. So if you look at this chart here, this is an example network, VGG16. And in dark, so in black, you have actual runtime. Brown is our work, NeuralPower, and Paleo is prior work. As you can see, what is important here is to identify where does your machine learning model spend the most time, because this is the part that you would like potentially to optimize. So, you know, if you look at end-to-end latency for inference, for example, this is something you'd like to be able to make more efficient. If you look here, you can see that, in fact, the most of the bottleneck here is this fully connected layer 6 whereas the priori did not identify it as the bottleneck. It identified other layers as bottlenecks, which is clearly incorrect. So what I want you to take from here is that accuracy, even percentage accuracy, is not the most important, but what is important is the ability to take design decisions when looking at some sort of breakdown to see where the bottlenecks are. And from a similar standpoint, if you look at actual, so black and brown, NeuralPower results for power consumption, you can see that while results are not exactly the same, the actual ranking or importance in terms of power contribution in this power breakdown is maintained. So your bottleneck in terms of power are perhaps conv1, 2 and conv2, 2 layers, right? And this is, again, identified by both NeuralPower and the actual results. So it's important to preserve that reliability in the decision that you're going to take when trying to redesign the network. I would like to point out that these models are developed once for a given platform and then reused everywhere. When you put everything together in a network level fashion, so you basically add all per layer latencies to get end-to-end network latency, the results are even better, obviously. So here we have full networks. You have VGG16, AlexNet, and others. And compared to the original baseline that we compare against and the actual runtime, we are always very close, except for this particular one. For power, the results are even better. Again, NIN is the one that is the least accurate. However, most of the time in this particular case, it's almost the same as the actual power results. The way we gather power results is by using profiling on the platform. Energy would be the product between average power and average latency. And again, results are very good between the actual and predicted. And I would like to point out one more thing. Many times it's important to look not just at how energy efficient or how fast or how your memory footprint compares with a baseline, but at the same time, we'd like to see how much, say, energy do I spend per correct inference. Because I'll give you another example from the hardware design world. Typically, we look at energy delay product as a trade-off, right? So with like, on one hand, you want to minimize energy, but you also would like to minimize delay, but they are competing with each other. So typically, smaller models, in this case, might have better energy efficiency, but they may not be as good in terms of inference accuracy. So this is why it makes sense to look at some sort of trade-off energy precision ratio, so to speak. We define the energy precision ratio as the product between classification error and energy per inference, or energy per serving, for example. And we also have a coefficient here, alpha, that can vary. And if you increase its value, it's going to give more importance to classification accuracy as opposed to energy per inference. So this gives you an idea of a more balanced approach, where instead of going with only one constraint or one objective than the other, you look at a combined objective. So if you consider these three networks, the best in terms of accuracy, obviously, is VGG16, but it's the most energy costly. If you look at various values for alpha, where you give more importance to classification error or more importance to energy per inference, you can see that AlexNet becomes a choice by using this EPR ratio. Whereas if you only care, or you care mostly about classification accuracy or classification error, then VGG16 is the winner, despite its high energy inefficiency. So this kind of metric would allow you to parse the joint space of machine learning model and hardware together to identify configurations where you find a good trade-off between classification error and energy per inference, and hardware metrics. So now that we know how to characterize for a given platform, these machine learning models. We can think about how we can optimize it. So if we can measure these hardware metrics, we can, or we can characterize machine learning models from a hardware perspective, we can find ways to hone in these configurations here that are best in terms of both accuracy and hardware resource usage. Neural architecture search in general is at the point where it can be done in days. But in general, it brings 5 to 10 improvements in energy and latency if done properly. So this is where we wanted to make a difference. And our work actually pushed the days to hours. So you can actually do this efficient architecture search in a hardware-aware fashion much more efficiently and still get state-of-the-art results. So a little bit about neural architecture search, or it's also called AutoML. So in general, when we do mobile neural architecture search or mobile AutoML, we try to identify the configurations, machine learning models that fit a certain device. So it's a device-aware ConvNet model that we try to put on this device. So AutoML does this automatically in the sense that it allows you to search this space automatically and formulate it as an optimization problem. But what it does, it actually needs to specify first the search space. So the search space typically consists of these building blocks that you'll have in your neural network. So for example, it could include 3 by 3 to 7 by 7 conv layers. It could have fully connected layers. It could have separable convolution as a construct. It could have blocks that have residuals that you replicate. So the search space is basically what it's important, and it actually can change quite a bit the result of your neural architecture accuracy. What you need to do next is to employ some sort of optimization algorithm that is able to search efficiently. So you turn the search problem into an optimization problem by this selection problem into an optimization problem. And you have to do it in hardware-aware fashion, so you need to have these models that we just discussed, right? So it could be a latency model, could be an energy model, a memory footprint model. So you do this in hardware-aware for a given fashion for a given platform. The problem with that, as I mentioned, is that this is a very costly process. And we actually wanted to reduce this from hundreds of hours to just single digits, like hours, less than half a day, so to speak. So our question that we wanted to answer was, can we reduce the search cost from days down to hours? And the answer to that is yes, by looking at ways to make this search more efficient and by structuring perhaps the search space a little bit differently. So just a little bit of background, our approach comes from the part of neural architecture search that is differentiable, relies on differentiable NAS. One example is the multipath differentiable NAS approach, which actually tries to identify each of these components, the structure, by allowing multiple choices. For example, in layer I would like to see which of these conv layers I should use, 3 by 3, 5 by 5, or 7 by 7. And then what we end up here with is a supernet in which each candidate network is represented by a separate path, in this case, 3 paths. Then the architecture search problem becomes a path level selection problem, because imagine that each layer has to select between 3 candidates or 4 candidates. So for all of these, you're going to have an exponential size selection problem. Basically, the selection means that only one of these is selected. So it's a 0-1 programming, which we know is NP complete or NP hard. So in multipath differentiable NAS, you basically identify, you convert it to an optimization problem, basically a convex optimization problem with appropriate changes, and you identify which choices satisfy your accuracy constraint. The complexity is high because you have all these parameters here. You have 3, 5, however many choices per layer you have. You have to replicate all these weights. You need to find out the values of them, and you need to find out which is selected. So this is why combinatorially this is a very complex problem. Our approach decided to reduce the search space by allowing these selections to overlap in a single superkernel. So we assume that all these choices will have shared weights or shared parameters. In other words, the multipath selection problem becomes a selection of an inner or outer layer in this superkernel. So a 3x3 means I only select the inner one. A 5x5 means I select both the inner and the outer one. And then a 7x7 means I select all three. This inner one, the middle layer, and then the outer layer. In other words, what we do, because we're sharing these weights, we only need to care about the weights of the largest candidate operand only. So that makes the search more efficient. So this is a new type of encoding that we're using, and therefore, because we do this, we're able to reduce the search cost by more than 3 orders of magnitude and still get top state-of-the-art accuracy for ImageNet. So I'll give you an example. So, for example, the superkernel has to select between a 3x3 and 5x5. If we want 3x3, 3x3 is always selected, but the outer shell is not. For 5x5, we select always the inner kernel, but we also add the outer shell. The problem is you still have a 0-1 selection here, so it's still a 0-1 programming decision problem, which is it's not differentiable. So we can't throw any like stochastic gradient descent approach to it. So the way we get around that problem is we make the 0-1 selection differentiable by using group lasso and a trainable kernel threshold variable. So basically this is identified during training, and then we use this group lasso approach to make the 0-1 non-differentiable selection in a differentiable selection, and then we can put it in the cost function for SGD, for example. Similarly, you could use the same approach for expansion ratio, right? So this is an expansion ratio of 3, in which half of the channels are here, but half of the channels are not. An expansion ratio of 6, both of them are included. Or you can completely drop, in which case the selection variable is 0, and it doesn't really matter what the internal selection variables are. And then again, we use group lasso with two trainable threshold parameters here, and then again, we make it differentiable. So as you can imagine, all of these components could be part of this search space. So we do it for kernel size, expansion ratio, also squeeze excite ratio, and skip ops. Everything is part of the search space, and then we use stochastic gradient descent. This is part of the objective function, and the way we define the objective function is by adding to the cross entropy loss, which is typically attached to the machine learning model accuracy, a trade-off parameter, a lambda multiplied by the latency. And for the latency, you can assume you have this model that you have developed. So the idea is you minimize both the cross entropy loss as well as the target latency, and depending on the lambda value, you could give more weight to accuracy or to hardware latency. Now, in this particular example, the hardware platform we used is a Pixel 1 phone. So we profiled all these types of layers on this platform, and we came up, because it was a very simple, we only looked at latency, we decided to use just a simple lookup table rather than do model selection like I mentioned before. So for all the different options that we had in terms of different layers, we profiled these latencies. And we put it together, again, in a model that it is part, like you've seen before, it is part of the differentiable search. So the runtime is basically, in general, is the 3x3 latency plus whether we use the outer layer, meaning outer layer is this one here, then we're going to add this correction latency term. And this way, we actually get a pretty good agreement between the measured and predicted runtime on the Pixel 1 platform. You can repeat the same. You can do the same for energy. You can do the same for memory footprint, as long as you have these actual numbers that you can populate in this model, hardware model that you have. So how good is all this? We compare here standalone neural architecture search methods in terms of their search cost in number of epochs, as well as accuracy. So these are the actual results published by the papers. We also have the manual designs, MobileNet v2, MobileNet v3. We call them manual designs because they are not the result of a neural architecture search. The search cost is not really zero because it does involve a lot of manuals. A lot of engineers actually worked to find these configurations. But from a search cost perspective, there was no automation or no automated cost associated with identifying these networks. Multi-path NAS, which is where our work falls under, are here. So they are better in terms of search cost. Our work turns out that is able to be much more efficient in terms of search cost. And note here that the search cost in epochs is log scale. And at the same time is able to achieve for ImageNet top 1 accuracy, while also satisfying this 80 millisecond runtime constraint that all of these were able to achieve. Not only that, single-path NAS is better than the manual designs, MobileNet v2, v3 in terms of accuracy, but at the same time is much faster than other NAS approaches, while achieving 3 orders of magnitude, more than 3 orders of magnitude reduction in the search cost. So instead of waiting days, you can do this in a matter of hours. So this is great news. So once you identify this configuration that satisfies your hardware constraints as well as achieves best accuracy, the question is, what is next? What else can we do? Suppose you do this, but then maybe the model runs fine on your smartphone, but if you want to deploy it on your watch, you're going to incur even further resource reductions, resource constraints. So can you do better? Can you make these networks that you identified even better in terms of hardware efficiency? And this is where cutting down the model size comes into the picture. So I'm going to feature a couple of our recent works on quantization, so flight, and then I'll explain what that is, and ledger, which is network pruning. And both actually aim to push this trade-off between test error and power memory footprint further down, meaning for the same accuracy, you're actually able to get less power cost or less memory or less latency. And we were able to get 2 orders of magnitude lower energy and much less area. So for example, imagine a tiny edge device. It would be able to run this in a tiny silicon space with minimal loss in accuracy. So, so if you look at the spectrum of these lightweight neural networks that we have, you start with full precision. These are pretty costly in terms of power or memory cost. Typically, people look at ways to make them more lightweight. So we call this light NN 1, light NN 2, and the 1 or 2 corresponds to the number of bits, 1 bits that are used for representing the weight. Of course, you also have a gap between. So the question is, can we fill this gap? Because sometimes you like to be close to full precision error, but you'd like to reduce the power memory cost a little bit. The other thing is binarized neural networks are an option, right? You could use that to some extent, but it might lose quite a bit of accuracy. Our work aims to push these light NN approaches closer to lower or higher accuracy, lower test error, as well as the binarized approaches as well. So I'll give you a few examples. So in general, light NN, the way we envision it is, the idea is like others, we try to replace multipliers that are expensive with a limited number of shift and add operators. So if you think in terms of the sign representation for a weight, this is typically, you have the sign and you have this weight represented as a sum of powers of 2. And the idea is each of these powers of 2, it is shift is represented by a shift by some number, but we constrain the number of bits to represent the weight to be only 1 or 2. So we find the closest from a stochastic rounding perspective, the closest representation that uses exactly 1 power of 2 or 2 powers of 2 to the actual weight. If you go from the conventional neuron that does this weighted sum using MAC operations, if you just do shift and add with a light and 2, you will have only 2 shifts and an add. And again, here, 2 shifts and an add. So much cheaper. So that's the idea. The way training works, in the forward path, we do stochastic rounding for the weight using either 1 or 2 powers of 2. We compute in the backward path, we do floating point gradient, so we switch back to floating point. We update the weights, and then again we round. And then when this ends, when proper accuracy is achieved. Typically, results are very good in the case that you do fill the gap between conventional full precision and binarized neural networks. As you can see here, the accuracy loss achieved by binarized is actually recovered by light and approaches. So this is great. In addition, if you look at how for MNIST and Cypher10 and ImageNet is also consistent to this, these lightweight quantized representations, which are the red, all the red points here, allow you to have more Pareto optimal configurations, which are indicated by the triangles. Blue is conventional, meaning full precision. So as you can see here, you have a lot more options. As a designer, you may want to say, okay, this is actually log scale in terms of energy, so I do have quite a bit of choices here, and they're all at the lowest test error. Same here, right? And for example, this configuration and this configuration, you have 2 orders of magnitude in energy reduction without losing any of the accuracy, right? So this is a win for designers that would like to have more freedom in achieving their constraints. Now, can we do better than this? And the answer is yes, we can push this to a flight and end, so a flexible approach. In light and N2, all your weights use exactly 2 powers of 2. In light and NY, use exactly 1 power of 1, 1 power of 2. So a flexible or a flight and N would allow you to be somewhere in between. So light and N1 filters use only 1 power of 2. So 1 over 2, 1 over 4, so on and so forth. Light and N2 use a combination. So this is 1 over 8, and this is 1 over 8 plus 1 over 4, and so on and so forth. A flight and N would allow you to mix. And the way you identify which part uses light and N1 or light and N2 is during training. You identify which of the 2 options is best for accuracy. So by doing so, you're able to not lose much in terms of efficiency, hardware efficiency, but you gain quite a bit in terms of accuracy. So here's how. Light and N2 is blue, light and N1 is red, but flight and N is actually better, right? So flight and N allows you to recover the accuracy loss from either the fixed of the 2 fixed approaches and gets to the best of the 2 for a given storage constraint. So it's able to be best. And finally, on the quantization front, binarized neural networks, typically when you train binarized neural networks, you'll end up with quite a bit of loss in accuracy. And the reason for that is because there are, during training, there are issues that basically make the distribution of your weight, instead of being plus minus 1 normally distributed, they shift them, and that generates problems in accuracy during training. So what we do, we use regularizing for the activation distribution to be able to reduce the impact of that on overall accuracy. And the results are very good in that sense. So these are binarized neural network approaches. and we're able to recover for both top 1 and top 5 anywhere from 6, 7 to maybe around that 6 to 7%, 2 to 7% accuracy. So this is quite important, while at the same time keeping the model size very small. And the last, and I think we have a few more minutes, so I want to talk a little bit about pruning. So this pushed the Pareto front further here, but pruning allows you to change the requirements for your model quite a bit. So filter or channel pruning allows you to change the structure of the neural network by pruning away channels that do not impact accuracy quite a bit. So by pruning channels, you do reduce computation and storage. However, that may hurt accuracy. So many times you need to retrain or fine tune, right? So you fine tune and then you recover some of the accuracy loss. In many cases, pruning allows you to reduce significantly the model size, memory footprint, latency, everything, and recover the entire accuracy through fine tuning. The problem is this fine tuning actually requires quite a bit of work. So if you have an application, right, where you need to identify upfront, well, I'll give you an example. My product line actually spans a bunch of platforms that have different computation requirements or capabilities. So you might have a platform for which you can basically do a little bit of pruning. For another one, you can do more. And for others, you have to do quite a bit of pruning. The problem is you need to identify this trade-off curve to see how well you can trade off accuracy and flop count. But at the same time, doing this repeatedly might take quite a bit of time, because every time you need to set a different set of constraints and you need to figure out how to do pruning. So that created a question in our mind: can we do this more efficiently? In other words, instead of doing this for every single platform, every time repeat the process, can we do this once and reuse the work? And this actually is important, because in many applications we do not know, we do not have this prior or a priori, we don't have this target flop count or accuracy for our particular application. This is especially true for applications depicted here, where you have embodied AI applications where both time to destination and the closest to destination are important. So this is especially important in autonomous UAV robotics applications. So with that in mind, we looked at ways to turn this problem, where you prune, you evaluate, and then you iterate until you find the best pruned network that satisfies your constraints and your accuracy, into an approach where you start with the kinds of flop counts that you need, and you do this once, and you identify what are the levels of pruning that satisfy your flop count constraints once. So once you do it, you have them, and you don't have to repeat it again. And you do it at the cost of doing only one iteration here. So in other words, it gives you the entire curve for the cost of 1 point on that curve. Just to give you an idea, this global ranking, or learning a global ranking, which we call it Ledger, tries to learn the importance of the filters. So from low importance to high importance, such that when we have a flop count target, say we can prune the low importance ones. And then if we have not an 80% flop count, but maybe a 30% flop count, we can prune further. So once we learn this ranking once, we can go on this in this ranking and say, okay, here I'm gonna do the best I can. So it's a best effort kind of approach, maximum accuracy for this flop count. As we know, anything about machine learning is hard. So learning the right ranking is also hard. The complexity is quite high, but we use prior work that showed that L2 norms of filter weights can accurately rank filters in an intralayer fashion. So we use a layer-wise thin transformation to go from the L2 norms of the filter weights to this ranking. And we learn this transformation such that we maximize the overall accuracy that allows us to filter or to rank these layers for a given flop count, right? So for example, you go from the original layers, you use this learned alpha K pair for this affine transformation, and then the result is these channels are ranked accordingly such that they can be pruned for a target pruning flop count. The results are quite good. So Ledger is able, and this was published this year in CVPR. Ledger is able to achieve state-of-the-art compared to other approaches. So the accuracy is best across the board, while also achieving the lowest flop count overall. So it is quite good. It's a nice, interesting idea for learning once and then reusing it over again. And if you look at how it compares across different platforms and different types of networks, overall, you can see that this channel pruning introduces an almost linear relationship between flop count and latency, which is great because you can use flop count as a proxy for latency, for example, or perhaps through another transformation, flop count to energy or memory footprint. So we put together the three components, the modeling, the optimization, as well as additional cutting down the model size. And the good news is that we can expect to do this search fast by virtue of these efficient hardware metric models that we learn once, by virtue of a single path NAS approach that is efficient, and further achieve up to 2 orders of magnitude efficiency in the model hardware metric characteristics while not, cutting back on accuracy. So this is really something that can take us at the putting together both the hardware and the machine learning together in a co-design approach. So if you were to put this together in a platform that would actually push everything in on edge devices, eventually speech recognition would run on your smartwatch. And when you ask the question, "What's my name?" My watch would be able to actually say, "You're Diana. That's what you told me anyway. This is the correct answer, but I have to have my watch connected to my smartphone and my smartphone connected to the network." But the goal is to have full autonomy for these edge devices such that they can operate on their own. And with this, I'd like to conclude my talk. I would like to thank my collaborators at both Carnegie Mellon, my students at Carnegie Mellon, collaborators at Google, at Microsoft. And if you're interested, our webpage is ENIAC with a Y.org, and our code is available on GitHub. And also, I'm happy to take any questions now. Thank you.
Thank you, Diana, for the inspiring work. So now let's open it up for questions. We have received questions from Q&A. In case you haven't got chance to type your questions, you can do it now, or you can raise your hand. I will unmute you so that you can speak your questions. The first one will be Luke Zhang. Could you, I'm gonna pass it, I'm gonna unmute you so that,
Hi.
Hi.
Hey, my first question is about one of the work of yours work is NeuralPower.
Mm-hmm.
Okay, so in the work is states like the expressiveness and also it's like the reason to use the polynomial based prediction method is because it's adaptability. So you can shrink the expressiveness and also complexity of a node by your just like your own choice, and depends on the the application scenario. So do you think if we replace the polynomial based with a neural network, would that be more flexible, or would that cause any trouble? Because that's my naive thinking.
Mm-hmm. Yeah, I think that's a great question. So I think you're talking about this slide, right? So so the reason we decided to go with a polynomial model is because of its simplicity. It allowed us to do model selection, and the reason we added these additional terms related to clock count and the max count, actually multiply accumulate operations, was to show some compatibility with prior work. There's nothing preventing you from using a neural network instead of this. However, I want to say that it might be too much, depending on, I mean, you would have a lot more parameters to think about. So you would need to do, your model selection translates into a neural architecture search selection problem, right? Because you need to identify what neural network is good to model these. I believe there was some work from McGill a few years ago that was trying to model hardware metrics using neural networks. So it's not impossible. You can do it, but for us, it was just easier to do it this way.
Okay, thanks.
Sure.
So the next question, I think, is from Yonggang Fu. I think I have unmuted you, Yonggang. You can speak your question.
Sure, yeah. So actually, my question is similar with Luke's. So, hi, Professor. So I'm very interested also in your NeuralPower work, which provides a powerful hardware metric predictor. And my first question is that, according to your formulation here, so the NeuralPower framework assumes the layers are executed in a sequential manner, right? So, is it possible to extend it to a layer-wise pipeline execution pattern, which is very common on DNN for FPGAs?
Yeah. So this is a very good point. You would need to potentially slightly change. So actually, this assumes that you have a per layer model, and then it's a composable model. You put it together, and you basically add latency for each layer to find the end-to-end latency. That works fine for the networks we considered. I will tell you that for networks that have residual connections, that does not work as well. And the reason for that is when you have residual connections, though you need to basically store all that information until you do the merge, right? So what does it mean you have to store them? Well, it means that that is hardware usage. So that translates further into the runtime, into the power. So this is not going to work as defined here for any type of neural network architecture. So it is a methodology in the sense that you can adapt it to other types of neural network architectures. This is a good question. So you could apply it, but you would need to make changes to the model. So the model selection might be different. In that case, there would be some value in what Luke brought up. So you might move away from polynomial type models to something else, neural networks maybe, to capture runtime or power or energy. But that's correct. If you move away from layer-wise compositionality, then you from layer to blocks, for example, because in NAS you actually use blocks, and those blocks are actually replicated, right? So instead of using types of layers and characterize them separately, you would basically do this characterization for more complex blocks. So that's a good point. I don't know if that answered your question.
Yes, thank you. Got it.
Okay, sure.
To stay on the schedule, maybe we pick up the next 2 or 3 questions. The next one is from Chao Jianli. I think you can speak now.
Okay.
Okay.
So, hello, Professor Marculescu. I have a question on the paralyzed network in CVPR last year. I noticed that you mentioned there are 3 distribution problems that would cause the difficulties in training. But I'm not very clear about why the gradient mismatch problem will cause the difficulty in training, because I think if we use a real gradient instead of the ST function, all gradient will be zeros and the network cannot be null. And I think that's the reason why some previous work will use ST functions for binarized neural network training. So could we say such mismatch is helping in the training? So that's my confusing. I'm not clear about why such mismatch will make the difficulty in training.
Yeah, so I know exactly what you're saying. So I think in our particular case, in our particular scenario, and the way we basically, all these networks actually were considering the kind of training that would exhibit this gradient mismatch issue and the degeneration and saturation. So you're exactly right that if you address this some other way, you will not need to do this regularizing of the activation distribution. So if there is, it would be great to compare with that kind of approach. In our case, we just decided to stick to this for the ability to do this comparison. But I agree with you. This is something that that definitely can be done.
Okay, thank you. So, but we can still say the accuracy boosting from the accuracy, right?
I'm sorry, can you repeat the question?
Sorry. I say, although we are not very clear about why we fix the gradient mismatch problem will help on the accuracy, but
yes.
the experiment shows that it do have some benefit on the accuracy performance.
Yes.
Okay.
Correct. Yes. Yes.
Thank you.
And the next question is from Haoran Yu.
Yes. Hello, Professor. Can you hear me?
Yeah,
we can
hear you. Yeah.
I have a question for your single-path NAS work, and the result is quite surprisingly improved in terms of both the search cost and accuracy. But the comparison mostly based on the earlier NAS work. So I'm wondering about the comparison with sharing NAS. Could you comment on the difference between your single-path NAS and the with sharing NAS from both the technical and the performance aspect?
Sure. Yeah. So yeah, this work is from last year. So in between, like I said, in machine learning, things are happening at a very fast speed. So this was when this is what was available at the time. So our work was first published in September last year, and then we have a more expanded version in a journal. But that's a good point. And actually, there is work that compares with us. So I have become aware of it. So if you're interested, I can share. And they are, of course, they are improving on it. It's work that was published more recently. Actually, I don't know if it's published. Some of them are on archive, but they may not be properly peer-reviewed. But there is work that shows that you can improve on it. So let me explain why. Why at that point in time we may have gotten state-of-the-art accuracy in fast. So there are three things that are very important in NAS. One is how do you define your search space? So what are the components that you use to build your neural network, right? The second one is how do you do the search? So the optimization approach that you're using to identify the configuration that meets your accuracy. So when you look at these two, our approach was first, our search space was quite different, or in some sense different. I mean, there's maybe one or two approaches that are similar in the search space, because we did have components that you would see in MobileNet, V2, V3, whereas in others there weren't. So it was not really fair from that standpoint. The other thing that we did is we did the weight sharing, right, which most of the others don't. So the fact that we were able to be more efficient in identifying the configuration actually allows us to, so in this combination of making the search space different, making the search more efficient, we're able to explore perhaps more and able to identify something that is more accurate, right? The configuration that is more accurate. I'm not saying this is the end of it, right? You could take this approach and compare, but the thing is, like I said, none of these comparisons is apples to apples, including ours, right? Because the search space might be different, the approach by which you do the optimization might be different. And it would be interesting to look at which one might make more of a difference, right? Or do they make a difference when taken together? So I'm sure there's, I know at least two works that cite us and they improve on it. So yes, it's I am aware of those new results.
Yeah, thank you. Thank you for answering.
Thank you. I
Sure.
think we cover all the questions from the audience. Diana, if you still have time, I have one question.
Sure.
Thank
Yep.
you. So I really like you have the high level picture to put your work in the big picture to show where and how your work and have pushed forward the accuracy and efficiency trade-off. But I think that picture may also give an impression to us and especially students. You already done the work. So looking forward, what do you think the community is missing?
Yeah, we have not done the work, by the way. I mean, there's a lot of things that still have to be done, right? So we just touched the surface here, and I'm not the only one doing work in this space, right? So there are a lot of researchers, including at Rice. So you, Celine, and others are doing work in this space, and what we looked at here is a more principled way to identify what is the best co-design approach that might take us to identifying a good pair of hardware machine learning models for a given application. But there are many other things to think about. So a machine learning application never runs alone on a platform, right? So that is something that has to be taken into account. How will running multiple machine learning models for different tasks or for the same task, where you have the same machine learning model but for different things, speech recognition, for example, versus object detection, how would those operate together? So the other things to think about is these are, vanilla, approaches that look at image classification as the bread and butter. But if you want to be open to other kinds of, we have to be open to other kinds of applications. So moving to video object detection or 3D object detection, multimodal modalities that take us to the VR AR space. There's almost no work. I mean, very little work has been done in NAS for multimodal or multitask. When I say multimodal, I mean multiple data sets or types of data that we're looking at. It could also be multimodal, so you have different models doing different things. So that's another thing that is important. So this is really all wide open. And again, we're looking at deep learning, we're looking at neural networks. The reason these are so attractive is because we think we know or we understand how they work. We don't really, but we like the regularity and the fact that we know, what a convolution is, what a fully connected layer does, right? Or what a separable convolution is. So there are more understandable ways to characterize them from the hardware usage perspective. But if you move away from the typical neural network machine learning model, there's a wide variety of other things that we should look at. And I know they're harder to characterize from a hardware perspective, and maybe they're not as popular or buzzworthy as deep learning, which is deep neural networks, but they do exist. And I think this is where we can move forward into exploring those.
Inspiring. Thank you very much for sharing your
Sure.
thoughts, and also really appreciate you spend the time with us, and also the very great talk. It'd be great to have you visit us soon. It's very close.
Sure.
Yeah. And to stay on schedule, let's finish
I'm sorry, my
here.
dog is...
Yeah, thank you all very much for attending, and thanks a lot, Diana.
Thank you so much. Thank you.
Thank you.
Bye.
Mm-hmm.
Bye. Bye.